This is the last lecture of week 5. Today in this lecture we will again talk about some example of underdamped free vibration problem which will help us to clear the concepts that we have learned earlier. So, all of us must have seen this kind of doors which have a door closer or a door damper. So, a damper or a pneumatic damper is attached to a door which prevents the oscillation of the door when opened or closed. So, these dampers are nothing but a linear viscous damper which adds damping to the system or to the door in this case, and thus prevents oscillation of the system. So, we have an exactly similar problem here. So, you can see that there is a door and with a door damper there. So, what we have in this problem is that the mass of the door is given, which is 50 kg, and the moment of inertia, the second moment of inertia is given as 7.5 kg meter square. So, this moment of inertia is about the centroidal axis of the door. Now, what the problem is that, so the dimensions of the door are given, it is 2 meter in the height and 1 meter in the width, and there is a torsional stiffness of 25 Newton meter per radian. So, I will try to explain the problem. So, I have a door which has a door stopper, the dimension of the door is given, the width is 1 meter, the height is 2 meter, there are torsional hinges at the door, the usual common door. So, this hinges actually gives a torsional spring kind of, this can be easily modeled as a torsional spring. The spring is constant is 25 Newton meter per radian, and the weight of the door is 50 kg. The moment of inertia about the centroidal axis is 7.5 kg meter square. So, the angle, the degree of freedom in this case is the angle that the door. So, what will happen whenever some excitation is given to the door will be free to rotate about the hinge, about this line it will be free to rotate. Okay. So, and it is free to oscillate about this axis, and therefore, this angle theta that the door, this angle theta that the door makes with the closed position of the door can be taken as a degree of freedom. So, this theta is going to be my degree of freedom. Okay. So, what is happening is that I have a door, I have all the necessary information about the door. Now, the problem statement is that we have to find out the damping coefficient. Okay. So, the damping, so we will assume linear viscous damping. So, the damping force F d is going to be some damping coefficient C t into the angular velocity theta dot. So, we have to find out this C t, this C t needs to be figured out so that the system is critically damped. That is the first part of the problem. The second part of the problem is that if a man pushes, the door is initially closed, now the man pushes the door with a certain angular velocity such that the door opens by 70 degree. Right. So, suppose a man is trying to enter through the door, he pushes the door with a certain angular velocity, and because of this angular velocity, the door should at least open by 70 degree. Okay. So, our job is to find out the angular velocity theta dot 0. Okay. The initial angular velocity that has to be imparted to the door. So, this being the problem, let us try to solve this problem. So, what should we need to do first? We should find out the equation of motion of the system. So, let us find out the equation of motion. So, once we find out the equation of motion, then only we will be able to find out the response of the system because of a given initial condition, and therefore, we can find out what needs to be the initial condition to open the door by 70 degree. Okay. So, let us first do the first part of the problem, where we need to find out the damping coefficient C t given that it is critically damped. So, what is meant by critically damped system? The damping factor or the damping ratio is going to be 1. So, that is what is given, and I need to find out what is going to be C t for zeta equals to 1. Okay. So, let us write down the equation of motion. So, this is here the degree of freedom is an angle theta. Therefore, the equation of motion will be in terms of moment. Okay. So, I can even draw the free body diagram, but since this is a simple case, I mean I might not need to draw a free body diagram, but you are free to draw a free body diagram. So, let me write down the equation of motion. So, I need the moment of inertia about the axis of the rotation. So, I need to find out, so theta is about the axis, about the hinge of the door, right. So, because it is about the hinge of the door, I need to find out the moment of inertia. So, this is the moment of inertia about the hinge or about where the rotation is, about the axis about which the rotation is happening. Okay. Hinge axis. So, let me call this as hinge axis. Okay. IC is about the centroidal axis and MD square is translating it to the hinge axis. Then I have CT into theta dot, where CT is the damping coefficient given by the door stopper, the pneumatic door stopper, and then I of course has the spring moment, so which is KT into theta. Okay. So, that is equal to 0 since no external moment is applied to the system. So, let me first find out these parameters. Okay. So, what is IC? IC is given as 7.5 kg meter square. What is MD square? MD square, M is given as 50 kg and D is the distance from the hinge, the distance of the centroidal axis from the hinge. So, width of the beam is 1.0 by 2 into square. So, if I evaluate this, this should be equal to 12.5 kg meter square. Okay. So, my total inertia, moment of inertia is going to be ICMD square, which is going to be this plus this. So, 19.5 kg meter square. Okay. And KT is given as 25 Newton meter per radian. Okay. So, now as we have done earlier, this equation can actually be written as theta double dot plus 2 zeta into omega n into theta dot plus omega n square into theta is equal to 0, where omega n square is nothing but KT by IC plus MD square and 2 zeta omega n is nothing but CT by IC plus MD square. Okay. So, in this equation I can I know the value of zeta, I can find, so I know the value of zeta, I can find out the value of omega n or the natural frequency from this problem. I know this value, so I can evaluate Ct. Okay. So, let me first find out what is the natural frequency. So, natural frequency omega n square is therefore 25 by 19.5, okay, which implies that omega n is nothing but square root of this, which is going to be 1.13. So, if you evaluate this, you will see it is 1.13 radian per second. So, this is my natural frequency. Okay. So, once I have got the natural frequency, then what is going to, then I will use this equation. So, I have 2, zeta is equal to 1 because this is critically damped system, omega n is 1.13. Okay, and that is equal to Ct, which is unknown and I need to evaluate, and Ic plus Md square is 19.5. Okay. So, if I solve this expression, then Ct turns out to be 44.15 and the unit is going to be Newton meter into second by radian. So, that when I multiply Ct by theta dot, this second by radian square will be cancelled out and I will have an unit for a moment. Okay. So, Ct theta dot is going to be a moment and therefore, it is dimensionally correct. Okay. So, this is the answer for the first part of the problem. Okay. And we have also evaluated the natural frequency, which is 1.13 radian per second, right. So, so first part of the problem is done, which was pretty straightforward. So, now let us go into the second part of the problem. So, what does second part say? Second part says that we have to find out the initial velocity theta dot 0 or the initial velocity that has to be imparted to the door. This is what we need to find out. This is the problem statement. So, now how are we going to find it out? So, let us find out the response of the system. So, we know since it is a critically damped system, the response of the system, the response that we obtain by solving the equation of motion, okay, is going to be theta t. Since it is an critically damped system, it is going to be zeta is equal to 1. So, it is going to be e to the power minus omega n t into C1 plus C2 t. This we have evaluated earlier. We have talked a lot about why this is going to be the response. Now, I have to evaluate C1 and C2, which are not known to me in terms of the initial conditions. Okay. So, what are the initial conditions? Let me write down the initial conditions. So, the initial condition is that theta 0, that is the rotation or the displacement at t equals to 0 is 0. We are assuming that the door is closed, right. That is why the man is pushing the door to open it, right. So, assuming the door to be closed at t equals to 0. Okay. So, this is my initial condition 1. The next initial condition is the condition on the angular velocity, that is theta dot 0. So, theta dot 0 is not 0. This is the velocity that is imparted by the man on the door and this is my initial velocity, or I can let me again write it. the velocity, angular velocity of course, velocity imparted to the door by the man, imparted to the door by the man at t equals to 0. Okay. So, if this is the case, let us plug in this initial condition into this equation. So, if I plug this in into this equation, what do I get? What is theta 0? Theta 0 is going to be e to the power 0, that is 1, and then I have C 1. So, theta 0 is 0 and therefore, C 1 is equal to 0. So, my response can be simplified as theta t, C 1 is equal to 0, therefore, C 2 t into e to the power minus omega n t. So, this is my response. Then theta dot z, let me find out what is theta dot t. So, theta dot t is going to be C 2 e to the power minus omega n t and then minus omega n C 2 t into e to the power minus omega n t. I have just differentiated this. Then therefore, what is theta dot 0? Theta dot 0 is going to be C 2 minus omega in minus omega t omega n into C 2 and that is equal to 0. So, this is 0 and that is equal to theta dot 0. Okay. So, C 2, therefore, C 2 is equal to theta dot 0. Therefore, my response ends up being theta dot 0 t e to the power minus omega n t. Okay. So, this is my response in terms of my initial velocity t. Now, I have got the response in terms of velocity. Now, I have to see that this response, what is theta dot 0, so that the door opens by 70 degree. What does that mean mathematically? Mathematically, it means that the maximum displacement that is obtained from this response based on theta dot 0 should be equal to 70 degree. Okay. So, let us find out when the maximum displacement is going to happen. So, to find out maximum, so we need to find out when is the maximum displacement or maximum theta is going to happen. So, in case of maximum displacement, to find out, let us see when does theta d theta dt becomes equal to 0. Okay. So, that is obtained by differentiating this and equating it to 0. So, if I differentiate it, I have theta dot 0 e to the power minus omega n t and then I find minus theta dot 0 minus omega n t into e to the power minus omega n t, and that should be equal to 0. So, which gives us that e to the power minus omega n t cannot be equal to 0. Therefore, by solving this equation, we get t equals to 1 by omega n. So, therefore, at a time instant when t is equal to 1 by omega n, my theta is going to be maximum. Therefore, let me find out the maximum, let me just write this. This is the time instant when maximum displacement will happen, time instant of maximum theta t. Okay. So, let me find out theta t max therefore. Okay. So, theta t max is going to happen at t equals to 1 by omega n. And let me find out the value for that. So, that is going to be theta dot 0, t is 1 by omega n e to the power minus omega n into 1 by omega n, and that should be equal to 70 degree. So, 70 degree I have to write it in terms of radian. So, 2 pi by 360. Okay. So, if I solve this, I get theta dot 0 into e to the power minus 1 by omega n should be equal to 70 into 2 pi by 360 degree. Okay. So, this is the equation that I need to solve. Okay. So, if I solve this equation, you can find out that theta, if I just solve this equation, I can find out theta dot 0 is going to be, let me give you the value for theta dot 0. So, theta dot 0 is going to become 3.75 radian per second. So, this is the answer, right. So, so this omega n I know, omega n is nothing, I have evaluated earlier, omega n is 1.13 radian per second. I know the value of E. Okay. So, actually this e to the power minus 1 can actually be written down as E. Okay. I know the value of E. The value of E is 2.718. Okay. Therefore, theta dot can be evaluated as 3.75 radian per second. So, the velocity that the man should impact the door is 3.57 radian per second to open the door at least by 70 degree. Okay. So, with this example, I come to the end of week 1. Okay. Before we end, let me quickly summarize what we have learned in week 1, and then we will move to the next week of the course. So, what we have learned in the week 1, let me just summarize it. So, let me quickly summarize. Okay. In summary, what we have learned is free vibration, response of S dot. Of course, we have first learned what is degree of freedom, how to find out the equation of motion using D'Alembert's principle and dynamic equilibrium, how to solve several problems to find out the equation of motion, and then once we got the equation of motion, we solved it to find out the response of the system. So, first we found out the free vibration response of S dot under no damping, that is under undamped condition. Okay. Under undamped condition, that is zeta is equal to 0. So, in this condition we saw that the response u t is nothing but u 0 cos omega n t plus u dot 0 by omega n into sin omega n t, where u 0 is the initial displacement at t equals to 0, u dot 0 is the initial velocity at t equals to 0, omega n is the natural frequency, and that can actually be written as root over of k by m. Okay. Then we had moved to damped free vibration of damped free vibration of So, under this topic we have seen three cases where case 1 is underdamped, where zeta is less than 1. So, here we have found out that the response u t was e to the power minus zeta omega n t into u 0 cos omega d t plus u dot 0 plus zeta omega n u 0 by omega d into sin omega d t. The response here was oscillatory. Okay. Omega d is called the damped natural frequency, and that is slightly less than omega n, and which is given as omega n into 1 minus theta square. And then we have found out that second case was critically, case 2 was critically damped. Where with zeta equals to 1. So, there the response is u t is e to the power minus omega n t into C 1 plus C 2 t. Okay. This is non-oscillatory motion. Okay. And case 3 was that of overdamped system. That is zeta is greater than 1. Here we saw that the response is nothing but e to the power minus zeta omega n t into C 1 e to the power minus omega d t plus C 2 sin omega d e to the power omega d t. This is also non-oscillatory. Okay. So, with this we will end week 1. We will move into week 2, which will start with force vibration of single degree of freedom. Thank you.